In the winter of 1894, a 35-year-old astronomer named Herbert George Wainwright sat alone in the stone tower of the Royal Observatory at Greenwich, his breath visible in the lamplight, calculating numbers that would not be understood for another generation. The coal shortage that had plagued London that December meant the observatory operated with minimal heating, and Wainwright wore 3 woolen coats as he scratched equations onto paper, with fingers that trembled not from cold, but from the terrible implications of what he was discovering. He had been tasked by the Astronomer Royal with a seemingly mundane assignment: to refine the calculations of stellar distances using the new photographic plates that had just arrived from the manufacturers in Germany. But what he found in those measurements was something that contradicted every assumption about the eternal nature of the heavens that had been held since antiquity. The stars, he realized with growing horror, were not fixed in their celestial spheres, but were moving, and not just moving, but fleeing, rushing outward into the darkness like refugees from some cosmic catastrophe. Wainwright's hands shook as he recalculated the figures a 4th time, then a 5th, always arriving at the same impossible conclusion. If the stars were racing away from some central point, then time itself must have a beginning, and if it had a beginning, then by all logical necessity it must also have an end. The idea was heretical not merely in theological terms but in scientific ones, for the prevailing cosmology of the late Victorian era rested upon the assumption of an eternal, unchanging universe, a vast mechanism that had always existed and would always continue to exist, ticking away like the great clock at Westminster, but without need of any divine clockmaker to wind it. Wainwright knew that publishing his findings would invite ridicule from his colleagues, most of whom were already sceptical of the new photographic methods and preferred the traditional visual observations made through brass telescopes. He decided to keep his calculations private, locking them in a drawer of his desk where they would remain undiscovered until 1923, long after his death from tuberculosis in 1901, when a young graduate student sorting through the observatory's archives would find them and recognise their significance in light of Edwin Hubble's recent discoveries about the expansion of the universe. But in that cold December of 1894, Wainwright could only sit in the darkness and contemplate what his numbers meant. That the universe was like a watch slowly running down, its energy dissipating, its stars burning out one by one until nothing remained but cold, dead matter scattered across an infinite void. The question of cosmic endings had preoccupied human minds long before Wainwright's lonely vigil in Greenwich. And in the markets of ancient Babylon, around 2000 BCE, priests of Marduk had studied clay tablets inscribed with observations of Venus and Jupiter, searching for patterns that might reveal the intentions of the gods and the ultimate fate of creation. These priest astronomers, who wore robes of undyed linen and shaved their heads in accordance with temple regulations, believed that the universe operated in great cycles, each lasting 432,000 years, at the end of which the world would be destroyed by fire or flood and then recreated anew. The concept was not unique to Mesopotamia. In the Indus Valley, Brahmin scholars were developing similar ideas about cosmic cycles called kalpas, each representing the lifespan of the universe from creation to dissolution, lasting 4.32 billion years by their calculations, a number that would prove remarkably close to modern estimates of the age of the solar system. The Greeks, by contrast, were divided on the matter, with Heraclitus arguing that the cosmos was eternal fire, constantly transforming but never truly ending, while the Stoics believed that the universe would eventually be consumed in a great conflagration called ekpyrosis, after which it would be reborn in exactly the same form, repeating the same events with the same people in an eternal recurrence. In the Library of Alexandria, around 250 BCE, a Babylonian priest named Berossus, who had relocated to the Greek island of Kos to teach Chaldean astronomy, wrote a history of the world in which he described not only its creation, but its eventual destruction. Berossus claimed that when all the planets aligned in the constellation of Cancer, the world would burn, and when they aligned in Capricorn, it would drown. A theory that gained considerable traction among Hellenistic scholars, who saw in it a synthesis of Babylonian observational wisdom and Greek philosophical reasoning. His books, written in Greek and dedicated to King Antiochus II, were considered authoritative sources for centuries, though they survive now only in fragments quoted by later writers. What Berossus understood, and what many of his Greek contemporaries did not, was that astronomical observation was not merely about predicting eclipses or the positions of planets, but about reading the fundamental structure of time itself, about understanding that the universe had a grammar and syntax that could be decoded through patient observation and mathematical reasoning. The Roman poet Lucretius, writing in the 1st century BCE, took a different view entirely in his philosophical epic De Rerum Natura, arguing that the universe was composed of atoms moving through infinite void, that everything that existed was the product of random collisions and combinations, and that the world had not been created by gods, but had emerged spontaneously from chaos. Lucretius wrote with a passionate intensity unusual for scientific poetry, describing how the walls of the world would eventually crumble, how the mechanisms that sustained life would break down, how even the sun itself would one day exhaust its fuel and die. His work was considered dangerous by both pagan and Christian authorities, and for more than 1,000 years it existed in only a handful of copies hidden in monastery libraries, too valuable to destroy, but too heretical to openly circulate. When a Florentine book hunter named Poggio Bracciolini rediscovered a manuscript of Lucretius in a German monastery in 1417, he unknowingly set in motion a revolution in thought that would eventually lead to the modern scientific understanding of cosmic entropy and heat death. The medieval Christian cosmology that dominated European thought from roughly 500 to 1500 CE had little interest in the physical end of the universe, because it was preoccupied with the spiritual end of time, the apocalypse described in the book of Revelation, when Christ would return to judge the living and the dead and establish a new heaven and a new earth. Theologians at the University of Paris in the 13th century debated intricate questions about the nature of eternity and whether time would continue to exist after the Last Judgment, with some arguing that the blessed in heaven would experience a kind of timeless now, an eternal present moment, while others insisted that succession and change must continue even in paradise, because otherwise the blessed would be indistinguishable from stones. These debates, conducted in Latin in draughty lecture halls heated by charcoal braziers, might seem remote from questions of physical cosmology, but they establish crucial conceptual tools for thinking about infinity, eternity, and the relationship between time and existence that would later prove essential for scientific cosmology. In 1277, the Bishop of Paris, Etienne Tempier, issued a condemnation of 219 philosophical propositions, many of them derived from Aristotelian physics, including the claim that the universe was eternal and uncreated. This condemnation, motivated primarily by theological concerns about limiting God's omnipotence, had the unintended effect of liberating natural philosophers to imagine alternative cosmologies, including ones in which the universe had a beginning and an end. At the University of Oxford, scholars associated with Merton College began developing new mathematical tools for describing motion and change, introducing concepts like instantaneous velocity and uniform acceleration that would later become fundamental to physics. These men, who included Thomas Bradwardine, William Heytesbury and Richard Swineshead, were not experimentalists in the modern sense, but rather mathematical theologians who used geometry and arithmetic to explore the nature of the created world. Yet their work laid groundwork for understanding how physical processes could be described quantitatively and how systems could evolve over time. The Protestant Reformation of the 16th century brought with it a renewed interest in biblical prophecy and apocalyptic speculation, with reformers like Martin Luther and his followers calculating that the end of the world was imminent, perhaps within a generation or two. Luther himself believed he was living in the final days, and that the corruption of the Catholic Church was a sign of the approaching apocalypse. In Wittenberg, where Luther taught theology, his students compiled chronologies of world history based on biblical genealogies, calculating that the world had been created in 4000 BCE and would exist for 6,000 years in total, meaning the end would come around 2000 CE, a calculation that found its way into the margins of countless Bibles printed in the 16th and 17th centuries. These chronological calculations required sophisticated mathematical work, attempting to harmonize the different genealogies given in Hebrew and Greek versions of Scripture, to account for overlapping reigns of kings, and to correlate biblical events with known dates from Egyptian and Babylonian history. The scholars who performed these calculations were not naive fundamentalists, but learned men who knew Hebrew, Greek, and often Arabic, who corresponded with rabbis and Islamic scholars to compare chronological traditions, and who genuinely believed they were uncovering the temporal structure of God's plan for creation. Meanwhile, in the Ottoman Empire, astronomers at the observatory in Istanbul were pursuing very different questions about cosmic time. In 1577, the Sultan Murad III commissioned the construction of a new observatory under the direction of Taqi al-Din, an astronomer and engineer who had studied the works of both Islamic and European scientists. Taqi al-Din built sophisticated instruments, including a mechanical astronomical clock that could measure time to within a few seconds per day, and he used these tools to make precise observations of a great comet that appeared in 1577, calculating its orbit and attempting to determine whether comets were atmospheric phenomena, as Aristotle had claimed, or celestial bodies moving through the heavens. His work paralleled that of Tycho Brahe in Denmark, who was making similar observations of the same comet, and both men independently reached the conclusion that comets moved beyond the moon, thereby proving that the celestial spheres were not solid crystalline shells as medieval cosmology had maintained, but were somehow permeable or perhaps did not exist at all. Taqi al-Din's observatory, however, was destroyed in 1580 on the orders of the Sultan, who had been persuaded by conservative clerics that astronomical observation was a form of forbidden divination, and that the observatory had brought bad luck upon the empire. The instruments were dismantled, the books scattered, and Ottoman astronomy went into a decline from which it would not recover for centuries, a reminder that scientific progress has never been inevitable or unidirectional, but has always depended upon particular political, economic, and cultural conditions that can appear and disappear with shocking rapidity. In Prague, in the early years of the 17th century, Johannes Kepler served as imperial mathematician to Rudolf II, a melancholy and eccentric Habsburg emperor who filled his castle with alchemists, astrologers, artists, and natural philosophers. Kepler, who had trained as a Lutheran theologian before becoming a mathematician, believed that God had constructed the universe according to mathematical principles, and that by uncovering these principles, one could read the mind of the Creator. His first book, Mysterium Cosmographicum, published in 1596 when he was just 25, attempted to explain why there were exactly 6 planets, and why they were spaced at their particular distances from the Sun, by showing that the orbits could be modelled using the 5 Platonic solids nested inside one another like a cosmic Russian doll. The book was brilliant, original, and completely wrong, but it established Kepler as a major astronomical thinker and brought him to the attention of Tycho Brahe, the greatest observational astronomer of the age, who invited Kepler to join him in Prague. When Tycho died suddenly in 1601, possibly from a burst bladder after refusing to leave a banquet to urinate because it would have violated court etiquette, Kepler inherited his vast collection of astronomical observations and spent the next decade analysing them with obsessive precision, eventually discovering that planets move in ellipses rather than circles, and that they sweep out equal areas and equal times, laws that would later prove crucial for understanding orbital mechanics and the long-term stability or instability of planetary systems. Kepler also wrote extensively about the end of the world, calculating on the basis of biblical chronology and astronomical conjunctions that the apocalypse might occur in 1704, though he cautioned that such predictions were uncertain and that God might have reasons unknown to humanity for delaying or advancing the end. What particularly interested Kepler was the question of whether the universe was finite or infinite, because if it was infinite, then it should be filled with an infinite number of stars, and the night sky should be as bright as day, an argument that would later be formalized as Olbers' paradox. Kepler rejected the idea of an infinite universe on both theological and physical grounds, arguing that God would have created a finite cosmos with the Earth and humanity at its center of importance, if not of position, and that an infinite universe would be incompatible with the observed darkness of the night sky. He did not know that he was grappling with what would become one of the central problems of cosmology, the question of why the universe appears the way it does, why it has the structure and properties we observe rather than some other set of structures and properties. In England, around the same time, Francis Bacon was developing a new method for investigating nature, based on systematic observation and inductive reasoning rather than deductive logic, and appeals to ancient authority. Bacon, who served as Lord Chancellor under King James I until his conviction for accepting bribes in 1621, wrote extensively about the need to compile natural histories, comprehensive collections of observed facts about the natural world, organised by topic, from which general principles could be extracted. His vision was of a collaborative scientific enterprise that would take generations to complete, with teams of observers gathering data, experimenters testing hypotheses, and theorists synthesizing results into ever more comprehensive systems of knowledge. Bacon had little interest in abstract cosmological speculation about the end of the universe. He was focused on practical knowledge that could improve human life, on technologies for increasing agricultural yields, on methods for preserving food, on techniques for mining and metalworking. Yet his emphasis on empirical investigation and his rejection of sterile scholastic debate helped create the intellectual culture that would eventually make modern cosmology possible. The assumption that questions about the universe should be settled by observation and calculation, rather than by appeals to scripture or philosophy. The founding of the Royal Society in London in 1660 marked a turning point in the institutionalisation of this new approach to natural knowledge. The Society's early meetings, held in Gresham College and attended by natural philosophers, physicians, mathematicians, and wealthy amateurs, featured demonstrations of experiments, presentations of new observations, and discussions of theoretical questions. Robert Hooke, the Society's curator of experiments, was tasked with demonstrating 3 or 4 new experiments at each weekly meeting, a punishing schedule that drove him to investigate everything from the elasticity of springs to the structure of snowflakes, to the possibility of constructing a flying machine. In his Micrographia, published in 1665 and illustrated with stunning engravings based on microscopic observations, Hooke speculated about the nature of matter and heat, suggesting that fire was a kind of motion at the microscopic level, and that when something burned, it was being dissolved into smaller and smaller particles. This insight, crude though it was, pointed toward the concept of entropy and the second law of thermodynamics, the realization that heat flows from hot to cold. That order tends toward disorder, that the universe is running down like a clock that no one can rewind. Isaac Newton, who joined the Royal Society in 1672 and dominated it for the latter half of his life, transformed cosmology by showing that the same mathematical laws that governed falling apples and the orbits of moons also governed the motions of the planets and the structure of the solar system. His Principia Mathematica, published in 1687 after considerable prodding from Edmund Halley, who paid for the printing cost himself, demonstrated that gravity was a universal force acting between all masses according to a simple inverse square law, and that from this single principle one could derive Kepler's laws of planetary motion, the tides, the precession of the equinoxes, and the trajectories of comets. Newton himself believed that the solar system required occasional divine intervention to remain stable. that the gravitational perturbations of the planets would eventually accumulate and cause the system to fly apart or collapse unless God periodically reached in and adjusted things, a view that scandalized continental mathematicians like Leibniz, who insisted that a perfect creator would have designed a system that needed no maintenance. This debate was not merely theological hair-splitting, but touched on deep questions about determinism, stability, and the long-term fate of physical systems, questions that would be rigorously addressed only in the 19th century, with the development of celestial mechanics and chaos theory. In the coffee houses of London in the early 18th century, where merchants, philosophers, and men of letters gathered to discuss politics, trade, and natural philosophy over cups of coffee or chocolate, Newton's ideas about gravity and the stability of the solar system became topics of public conversation and speculation. At the Grecian coffee house near the Royal Exchange, habitués debated whether comets might one day strike the Earth, whether the moon was falling toward the Earth or moving away from it, whether the sun's heat would eventually be exhausted. These were not academic debates, but reflected genuine public interest in cosmological questions, fueled by the publication of popular astronomy books and by the growing recognition that the universe operated according to natural laws that could be understood through mathematics and observation. The philosopher and physician David Hartley, writing in the 1740s, suggested that just as individual humans are born, mature, and die, so too might the entire solar system have a life cycle, eventually exhausting the sun's fuel and cooling into darkness. This idea of cosmic death was disturbing to many of his contemporaries, who preferred to believe that the universe was eternal, or at least that it would last until the biblical apocalypse. But Hartley insisted that observation and reason pointed toward a material universe governed by natural processes that must eventually run their course. The Industrial Revolution, which began in Britain in the late 18th century and spread across Europe and North America over the following decades, fundamentally changed humanity's relationship with energy and time. The development of the steam engine, pioneered by Thomas Newcomen and James Watt, made it possible to convert heat into mechanical work, to pump water out of mines, to drive textile machinery, to power locomotives and ships. Engineers working with these machines quickly realized that there were limits to efficiency, that not all the heat produced by burning coal could be converted into useful work, that some energy was always lost to the surroundings. In France, a young engineer named Sadi Carnot, son of a revolutionary general and himself a graduate of the École Polytechnique, published a brief treatise in 1824 titled Reflections on the Motive Power of Fire, in which he analysed the theoretical limits of heat engine efficiency. Carnot showed that the maximum possible efficiency of any heat engine depended only on the temperatures of the hot and cold reservoirs between which it operated, and that this maximum could never be reached in practice because of various irreversibilities and frictions. His work sold almost no copies during his lifetime, and was largely forgotten until the 1840s, when physicists began to realise that Carnot had discovered something fundamental about the nature of heat and energy. The formulation of the second law of thermodynamics in the 1850s by Rudolf Clausius in Germany and William Thomson, Lord Kelvin, in Britain, represented a turning point in cosmological thought, comparable to Newton's law of gravitation. The second law states that in any isolated system, entropy, a measure of disorder or randomness, always increases over time, that heat flows spontaneously from hot to cold, but not the reverse, that you cannot unscramble an egg or unburn a piece of wood. Thomson recognized immediately that if the second law applied to the universe as a whole, then the universe must be running down, its energy becoming more and more uniformly distributed, and therefore less and less useful for doing work. In a paper published in 1852, Thomson calculated that the sun was gradually cooling, and that eventually it would become too cold to support life on Earth, an idea that became known as the heat death of the universe. This was not a sudden catastrophic end, but a slow, inexorable slide into a state of maximum entropy, in which all temperatures would equalize, all chemical reactions would cease, and the universe would become a cold, dark, featureless void in which nothing could ever happen again. The idea was profoundly disturbing to Victorian sensibilities, which generally preferred to believe in progress, in the gradual improvement of human society, in a universe that was either eternal or at least would end in some kind of divine transformation rather than mere thermodynamic exhaustion. The discovery of radioactivity by Henri Becquerel in 1896 and its subsequent investigation by Marie and Pierre Curie and Ernest Rutherford complicated the picture by revealing a previously unknown source of energy. Rutherford, working at McGill University in Montreal and later at the University of Manchester, realised that radioactive decay was releasing enormous amounts of energy from within atoms, and that this process could extend the lifetime of the Sun far beyond what Thomson's calculations had suggested. In 1904, Rutherford gave a lecture at the Royal Institution in London in which he mentioned, somewhat nervously because Lord Kelvin was sitting in the front row, that the discovery of radioactivity meant that Kelvin's estimate of the Earth's age based on cooling rates was probably wrong. To Rutherford's relief, Kelvin, who was by then in his 80s, responded graciously, acknowledging that new discoveries required revising old conclusions. The realization that radioactive elements in the Earth's crust and mantle could generate heat meant that the planet was much older than Kelvin had calculated, and geological and paleontological evidence was increasingly pointing toward an age measured in billions, rather than millions of years, a timescale that seemed almost incomprehensible to early 20th century scientists accustomed to thinking in terms of recorded human history, spanning only a few thousand years. Meanwhile, the development of atomic theory and quantum mechanics in the early 20th century was revealing that matter and energy behaved in ways that seemed to violate common sense and classical physics. In Berlin, Max Planck had reluctantly concluded in 1900 that to explain the spectrum of black body radiation, one had to assume that energy was emitted and absorbed in discrete packets or quanta rather than continuously, an idea that seemed to contradict everything known about waves and oscillations. Albert Einstein, working as a patent examiner in Bern, Switzerland, took Planck's quantum hypothesis seriously and used it in 1905 to explain the photoelectric effect, showing that light itself came in discrete particles or photons, each with an energy proportional to its frequency. These discoveries suggested that at the atomic scale, nature was fundamentally discontinuous and probabilistic rather than smooth and deterministic, a realization that would eventually transform cosmology by revealing that seemingly stable atoms were actually dynamic systems in which electrons occupied discrete energy levels and could jump between them by emitting or absorbing photons. The person who would do more than anyone else to transform our understanding of the universe's structure and fate was a lawyer's son from Missouri named Edwin Hubble, who after studying law at Oxford and serving briefly in World War I, became an astronomer at the Mount Wilson Observatory in California. In the 1920s, Mount Wilson housed the world's largest telescope, a 100-inch reflector that could gather enough light to photograph faint galaxies and resolve individual stars within them. Hubble used this telescope to study what were then called spiral nebulae, cloud-like objects whose nature was hotly debated, with some astronomers believing they were gas clouds within our own Milky Way galaxy, and others arguing they were separate galaxies far beyond the Milky Way. In 1924, Hubble succeeded in identifying Cepheid variable stars in the Andromeda Nebula, stars whose intrinsic brightness could be determined from their pulsation period, allowing their distance to be calculated from their apparent brightness. The distance he calculated was so enormous that it proved conclusively that Andromeda was a separate galaxy, comparable in size to the Milky Way but located about 1 million light-years away, a discovery that expanded the known universe by a factor of roughly 1,000. Even more significant was Hubble's discovery, announced in 1929, that galaxies were moving away from us with velocities proportional to their distances, a relationship now known as Hubble's law. This was the observational confirmation of what Wainwright had glimpsed in his calculations 35 years earlier. The universe was expanding. The implications were staggering because if the universe was expanding, then running time backward would show all the galaxies converging toward a single point, suggesting that the universe had a beginning in a moment of creation that the Belgian priest and physicist Georges Lemaitre called the primeval atom, and that would later be mockingly referred to by Fred Hoyle as the Big Bang, a name that stuck despite its facetious origins. The idea that the universe had a definite beginning was controversial among physicists and astronomers, many of whom preferred to believe in an eternal, steady-state universe. But the evidence from galaxy redshifts kept accumulating, and by the 1960s the Big Bang theory had become the dominant cosmological model. The discovery of the cosmic microwave background radiation in 1964 by Arno Penzias and Robert Wilson, two radio astronomers working for Bell Laboratories in New Jersey, provided conclusive evidence for the Big Bang. Penzias and Wilson had been trying to eliminate sources of noise from a sensitive radio antenna, originally built for satellite communications, when they detected a faint uniform signal coming from all directions in the sky. After ruling out various sources of interference, including famously pigeon droppings on the antenna, they consulted with physicists at nearby Princeton University, who realized that what Penzias and Wilson had found was the relic radiation from the Big Bang itself, light from the early universe that had been stretched by cosmic expansion from visible wavelengths to microwaves. The temperature of this radiation was about 2.7 degrees above absolute zero, exactly what theorists had predicted for the cooled remnant of the hot, dense early universe. The discovery earned Penzias and Wilson the Nobel Prize and marked the definitive acceptance of the Big Bang theory as the correct description of cosmic origins. But if the universe had a beginning, what about its end? This question became increasingly urgent as cosmologists developed better measurements of cosmic expansion and better theoretical models of gravity and matter. Einstein's general theory of relativity, published in 1915, provided the mathematical framework for describing the geometry and evolution of the universe as a whole, treating space and time as a unified four-dimensional space-time that could be curved by the presence of matter and energy. Solutions to Einstein's equations showed that the universe could not be static, but must be either expanding or contracting, a conclusion that Einstein himself initially resisted, going so far as to introduce a cosmological constant term into his equations to allow for a static solution, a modification he later called his greatest blunder, when Hubble's observations showed that the universe was indeed expanding. The question of the universe's ultimate fate depended crucially on the average density of matter. If the density was high enough, gravity would eventually halt the expansion and cause the universe to recollapse in a big crunch, a time-reversed version of the Big Bang, in which all matter and energy would converge toward a singularity of infinite density and temperature. If the density was too low, the universe would expand forever, with galaxies becoming increasingly isolated as space stretched between them, stars eventually burning out and the universe ending in a cold, dark heat, death not unlike what Thomson had envisioned in the 19th century. Measuring the density of the universe proved to be extraordinarily difficult because most of the matter appeared to be invisible. In the 1970s, Vera Rubin and Kent Ford at the Carnegie Institution conducted careful observations of the rotation speeds of spiral galaxies and found something puzzling. Stars in the outer parts of galaxies were moving much faster than they should if the galaxy's mass was concentrated in its visible stars and gas. The only way to explain the observations was to assume that galaxies were surrounded by enormous halos of invisible dark matter that interacted gravitationally but did not emit light. Similar conclusions emerged from studies of galaxy clusters, which contained too little visible matter to hold themselves together gravitationally unless there was additional dark matter present. By the 1980s, it had become clear that the ordinary matter we can see, stars, gas, planets, people, constitutes only about 15% of the total matter in the universe, with the remaining 85% being some unknown form of dark matter, possibly exotic particles left over from the Big Bang that had never been detected in laboratory experiments. The question of cosmic fate took another unexpected turn in 1998, when two teams of astronomers studying distant supernova explosions announced that the expansion of the universe was not slowing down, as everyone had assumed, but was actually accelerating. The teams, led by Saul Perlmutter, Brian Schmidt and Adam Rees, had been using Type Ia supernovas as standard candles to measure cosmic distances and expansion rates at different epochs in cosmic history, expecting to determine how much gravity had slowed the expansion. Instead, they found that supernovae at moderate distances were fainter than expected, indicating they were farther away than predicted by a decelerating universe, which meant the expansion rate had increased over time. The discovery was so unexpected that both teams spent months checking their data and analysis for errors before announcing their results. But the conclusion was unavoidable. Some unknown form of energy, quickly dubbed dark energy, was causing space itself to expand at an accelerating rate. The nature of dark energy remains one of the deepest mysteries in physics, but its effect on the universe's fate is clear. If the acceleration continues, galaxies beyond our local group will eventually recede so fast that their light can never reach us. The universe will become increasingly dark and empty, and all structures, galaxies, stars, planets, atoms, will eventually be torn apart in a big rip. If the dark energy's strength increases with time, even if dark energy remains constant and structures are not torn apart, the long-term future of the universe in an accelerating expansion is bleak from the perspective of complex structures and life. Stars like the Sun have lifetimes measured in billions of years, but they are not eternal. The Sun itself will exhaust its hydrogen fuel in about 5 billion years, swell into a red giant that will engulf the inner planets, including Earth, then shed its outer layers and collapse into a white dwarf, a dense ember slowly cooling over trillions of years. More massive stars burn their fuel faster and end their lives in supernova explosions, leaving behind neutron stars or black holes. The smallest stars, red dwarfs with masses a tenth that of the Sun, burn so slowly that they can shine for trillions of years, far longer than the current age of the universe, but even they will eventually exhaust their fuel. After perhaps 100 trillion years, the last star will flicker out, and the universe will enter what has been called the degenerate era, in which the dominant objects are stellar remnants, white dwarfs, neutron stars and black holes, along with dead planets and diffuse clouds of gas and dust. During the degenerate era, which might last from 100 trillion to 1 million trillion years after the Big Bang, the remaining matter will continue to evolve, but extremely slowly. White dwarfs and neutron stars will continue to cool, radiating away their residual heat as infrared and eventually radio photons. Collisions between dead stars, though exceedingly rare given the vast distances involved, might occasionally create new bursts of energy. Black holes will be the most stable objects, immune to thermal cooling, but even they are not truly eternal. In 1974, Stephen Hawking discovered through a brilliant application of quantum mechanics that black holes must slowly evaporate by emitting thermal radiation, now called Hawking radiation, with a temperature inversely proportional to their mass. For a black hole with the mass of the Sun, this temperature is about 1/10,000,000th of a degree above absolute zero, far colder than the cosmic microwave background. So such black holes are currently absorbing more energy than they emit, and actually growing very slightly. But as the universe expands and cools, the background temperature will drop below the Hawking temperature, and black holes will begin to lose mass, slowly at first, then more rapidly as they shrink and their temperature increases. The evaporation time for a black hole scales as the cube of its mass, so stellar mass black holes will persist for about 10 to the 67 years, while the supermassive black holes at the centres of galaxies with masses millions or billions of times that of the Sun will last for 10 to the 99 years or longer. During these unimaginably long timescales, sometimes called the black hole era, the universe will be almost completely dark and empty, with occasional faint sparkles of Hawking radiation marking the final decay of these last remnants of collapsed stars. The final burst of radiation from an evaporating black hole will be spectacular on a microscopic scale, releasing as much energy as a thermonuclear bomb in a fraction of a second, but there will likely be nothing around to witness it. No observers, no instruments, no structures of any kind except perhaps some residual radiation and elementary particles scattered across vast distances. After the last black holes have evaporated perhaps 10 to the 100 years after the Big Bang, the universe will enter what has been termed the dark era, in which the only remaining objects are elementary particles, electrons, positrons, neutrinos, photons, spread so thinly that the average density is far lower than the best vacuum achievable in any laboratory. If protons are unstable, as suggested by some theories of particle physics, they will decay over timescales of perhaps 10 to the 36 years or longer, breaking down into lighter particles like positrons and neutrinos. In such a universe, matter as we know it simply does not exist. There are no atoms, no molecules, no possibilities for chemistry or life, or any kind of complex structure. The temperature will be indistinguishable from absolute zero, though quantum mechanics ensures that it can never quite reach zero exactly. Space will continue to expand, accelerated by dark energy, with any remaining particles becoming increasingly isolated from one another, causally disconnected as the space between them expands faster than light can travel. This vision of cosmic heat death, refined and quantified by modern physics, but fundamentally similar to what Thomson envisioned in the 19th century, raises profound questions about meaning and purpose in a universe that seems destined for maximum entropy and emptiness. Some physicists and philosophers have speculated about escape hatches or loopholes. Freeman Dyson, in a famous paper published in 1979, explored whether intelligent life might persist indefinitely in an ever-expanding cooling universe by slowing down its metabolism, becoming less and less active to conserve energy, essentially hibernating through longer and longer periods and awakening for shorter and shorter moments of thought, stretching a finite amount of usable energy across infinite subjective time. Dyson's calculations suggested this might work in a universe that expands forever but without acceleration, where the temperature approaches zero but useful energy gradients persist. However, in an accelerating universe dominated by dark energy, his scenario does not work because the dark energy provides a temperature floor below which the universe cannot cool, making true hibernation impossible. Other speculative scenarios involve the possibility of travelling to other universes or creating new universes. Some versions of quantum mechanics and string theory suggest that our universe might be just one of many in a vast multiverse, either existing in parallel or budding off from one another like bubbles in boiling water. If such other universes exist, and if there are ways to travel between them or to influence them, then perhaps intelligent life facing the end of one universe could escape to another, or could engineer the creation of a new universe with more favourable conditions. The physicist Lee Smolin has proposed a theory called cosmological natural selection, in which universes give birth to offspring universes through the formation of black holes, with the physical constants of the offspring universe being slightly different from those of the parent, leading to a kind of evolution favouring universes that produce many black holes. If this theory is correct, and if sufficiently advanced civilizations can control the parameters of offspring universes, then perhaps the end of our universe is not the end of all possibilities, but merely a transition to something new and different. Even more speculatively, some physicists have discussed whether advanced civilizations might manipulate the vacuum state of space itself, triggering a phase transition that could create a new inflationary epoch or even a new Big Bang. The vacuum of space, according to quantum field theory, is not truly empty, but seethes with virtual particles constantly appearing and disappearing, and it may exist in one of several possible energy states. If our vacuum is in a false vacuum state, a higher energy state than the true minimum, then it might be possible to trigger a decay to the true vacuum, releasing enormous energy in the process. Such a decay could either destroy our universe or transform it into something radically different, possibly creating conditions for new forms of structure and complexity. The ethical implications of intentionally triggering such a transition are staggering, as it would presumably destroy all existing structures and life forms, but for a civilization facing certain extinction as the universe approaches heat death, it might seem like the only option. The theological and philosophical implications of modern cosmology's predictions about cosmic endings have been the subject of considerable debate. For religious traditions that emphasize God's sovereignty over creation, the idea that the universe will simply run down according to thermodynamic law, rather than ending in divine judgment and transformation, can seem incomplete or unsatisfying, suggesting a cosmos abandoned by its creator. The theologian Wolfhart Pannenberg argued that Christian eschatology, with its emphasis on resurrection and the transformation of creation, points toward a reality beyond the physical universe described by science, suggesting that the heat death predicted by physics is not the final word, but merely describes what would happen if the universe were a closed system with no external intervention. Other theologians have been less comfortable with this dualism between scientific and religious accounts of cosmic endings, preferring to see scientific cosmology and theological eschatology as addressing different kinds of questions, with science describing the physical processes and theology addressing questions of meaning and purpose that lie beyond the scope of empirical investigation. Philosophers working in the analytic tradition have explored the implications of cosmic eschatology for ethics and meaning. If the universe is destined to end in heat death, does that make our actions ultimately meaningless, or can there be meaning within finite temporal contexts even if nothing lasts forever? Bertrand Russell, in his 1903 essay, A Free Man's Worship, confronted the idea of cosmic futility directly, arguing that precisely because the universe is indifferent to human values, we must create our own meaning through our actions and relationships, building what beauty and justice we can in the brief time available to us. More recent philosophers like Samuel Scheffler have argued that what gives our lives meaning is not that our effects persist forever, but that they connect us to ongoing projects and communities that extend beyond our individual lifetimes, a form of temporal embeddedness that provides sufficient meaning even in a mortal cosmos. The physicist Paul Davies has argued that the evolution of the universe from a low-entropy initial state to a high-entropy final state represents a kind of cosmic arrow of time, giving a direction to cosmic history and making possible the emergence of complex structures, life, and consciousness during the middle phase, when energy gradients exist and useful work can be done. From this perspective, the heat death is not simply an ending but the necessary counterpart to the Big Bang, the exhale following the inhale, and the meaning of the universe, if it has any, lies in what happens during the middle phase, in the billion-year process by which matter organizes itself into stars and galaxies, planets and organisms, brains and civilizations capable of comprehending their own origins and fate. The very fact that we exist as conscious beings capable of understanding cosmology is itself remarkable. A local and temporary violation of the general trend toward disorder, made possible by the flow of energy from the sun through the biosphere and out into space as waste heat. In recent decades, advances in observational cosmology have allowed increasingly precise measurements of the universe's composition, expansion rate, and ultimate fate. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck Observatory have mapped the cosmic microwave background with extraordinary precision, revealing tiny fluctuations in temperature that correspond to density variations in the early universe, the seeds from which galaxies would later grow. These measurements have allowed cosmologists to determine that the universe is spatially flat, or very nearly so, meaning that its geometry is Euclidean on large scales, that it is composed of about 68% dark energy, 27% dark matter, and only 5% ordinary matter, and that it is about 13.8 billion years old. Large surveys of galaxy positions and properties, like the Sloan Digital Sky Survey and the Dark Energy Survey, have mapped the three-dimensional distribution of matter across billions of light years, revealing the cosmic web of filaments and voids that characterizes the large-scale structure, and providing additional evidence for dark energy's effects on cosmic expansion. Despite these impressive observational achievements, fundamental questions about the universe's ultimate fate remain unanswered, because they depend on the nature of dark energy, which is still poorly understood. If dark energy is simply Einstein's cosmological constant, an intrinsic property of space that remains constant as the universe expands, then the universe will continue to accelerate indefinitely, with the acceleration rate remaining constant, leading eventually to a cold, dark, empty cosmos as described earlier. If dark energy is instead some kind of dynamic field, sometimes called quintessence, its strength might change over time, either increasing and leading to a big rip, in which space expands so rapidly that it tears apart galaxies, stars, planets, and eventually atoms themselves, or decreasing and potentially reversing, allowing gravity to halt the expansion and cause a big crunch. Current observations favour a cosmological constant, or something very close to it, but the uncertainties are still large enough that other possibilities cannot be completely ruled out. Another source of uncertainty is the possibility of vacuum decay or phase transitions. If our universe's vacuum is in a metastable state, it could spontaneously decay to a lower energy state, a process that would begin at some random point in space and expand outward at the speed of light, transforming the properties of particles and forces as it went. Such a vacuum bubble, once nucleated, would be absolutely unstable and would grow without limit, eventually consuming the entire observable universe. Inside the bubble, the laws of physics might be completely different, with different masses for particles, different strengths for forces, possibly no stable atoms or no way for complex structures to form. The universe inside the bubble might be inhospitable to life as we know it, or it might allow for new and different forms of complexity that we cannot currently imagine. Calculations suggest that if our vacuum is metastable, it might have a lifetime much longer than the current age of the universe, perhaps 10 to the 100 years or more. But there is also some probability that decay could happen much sooner, tomorrow, or a billion years from now, with no warning. The prospect of vacuum decay raises the disturbing possibility that the universe could end not in a slow, heat death, but in sudden catastrophic transformation, a bubble of different physics expanding at light speed and obliterating everything in its path. This scenario has been compared to Ragnarok or other mythological end-of-the-world scenarios, but unlike those myths, it emerges from sober calculations in quantum field theory, and is at least in principle testable through particle physics experiments and cosmological observations. Some physicists have speculated, only half-jokingly, that the Large Hadron Collider or future particle accelerators might trigger vacuum decay by creating extreme conditions that nucleate a bubble, though detailed calculations suggest that if our vacuum were that fragile, cosmic rays would have triggered decay long ago. Nonetheless, the possibility serves as a reminder that our understanding of fundamental physics is still incomplete, and that the universe might surprise us in ways we have not yet imagined. Yet another possible ending suggested by some versions of quantum mechanics and quantum gravity is the eternal recurrence or cyclical universe. Roger Penrose has proposed a cosmological model called conformal cyclic cosmology, in which the infinite future of one universe, when all matter has decayed and only massless photons remain in an ever-expanding space, is mathematically equivalent to the Big Bang of the next universe, creating an infinite sequence of cosmic cycles or aeons. In Penrose's model, the heat death of one aeon becomes the Big Bang of the next through a mathematical transformation that rescales distances with the cold, empty final state of one universe, providing the initial conditions for the next. This idea has the appeal of avoiding both an absolute beginning and an absolute end, but it requires accepting some unconventional assumptions about the nature of time and the behaviour of matter in the far future, and it remains speculative and controversial among cosmologists. Loop quantum gravity, an alternative approach to quantum gravity, suggests a different kind of cyclical cosmology in which the Big Bang was actually a big bounce, the transition point of a previous contracting universe that reached a minimum size and then began expanding again. In this scenario, gravity becomes repulsive at extremely high densities, preventing the singularity that appears in classical general relativity and allowing the universe to bounce between expansion and contraction phases indefinitely. The model predicts that information about the previous cycle is largely erased during the bounce, so each cycle begins with nearly the same initial conditions, but some subtle traces might remain encoded in the cosmic microwave background or the distribution of galaxies. Like Penrose's conformal cyclic cosmology, loop quantum cosmology remains speculative, and it is unclear whether observations could ever definitively confirm or rule out such models. The search for answers to these questions about the universe's ultimate fate has driven the development of new telescopes and observatories operating across the electromagnetic spectrum and beyond. The James Webb Space Telescope, launched in 2021, has been observing the most distant galaxies ever seen, galaxies whose light has been travelling toward us for more than 13 billion years, showing us what the universe looked like when it was only a few 100 million years old. These observations provide crucial information about how the first stars and galaxies formed and how the universe evolved from the nearly uniform state revealed by the cosmic microwave background to the complex web of structures we see today. Ground-based telescopes like the extremely large telescope under construction in Chile will provide even higher resolution images and spectra, allowing astronomers to study the properties of dark matter and dark energy with unprecedented precision. Gravitational wave observatories like LIGO and Virgo have opened an entirely new window on the universe, detecting ripples in space-time produced by colliding black holes and neutron stars. These observations provide information about the universe that is completely independent of electromagnetic radiation, and may eventually allow cosmologists to probe epochs and events that are inaccessible to traditional telescopes, such as the first fraction of a second after the Big Bang or the interior structure of black holes. Future space-based gravitational wave observatories like LISA will be sensitive to lower frequency gravitational waves produced by supermassive black hole mergers and possibly by exotic sources from the early universe like cosmic strings or phase transitions. The combination of electromagnetic observations, gravitational wave detections, and possibly neutrino astronomy and cosmic ray studies will provide an increasingly complete picture of the universe's composition, history, and fate. Despite these technological advances, some questions about the universe's ultimate fate may be fundamentally unanswerable, not because of technological limitations, but because of the nature of cosmic expansion itself. In an accelerating universe, there is a cosmic event horizon, a distance beyond which light emitted now will never be able to reach us because the space between us and the source is expanding faster than light can travel. This horizon is currently about 16 billion light-years away, but it is shrinking as acceleration continues, meaning that galaxies now beyond the horizon are permanently beyond our observational reach, no matter how long we wait or how sensitive our instruments become. Information about what happens in those distant regions can never reach us, making it impossible to test cosmological theories that make predictions about the universe beyond our horizon. We are in effect trapped inside an observational bubble that is getting smaller with time, with more and more of the universe passing beyond our ability to observe. This limited observational horizon raises profound questions about the nature of scientific knowledge and the status of cosmological theories. Science is traditionally based on the principle that theories must be testable through observation and experiment. But if large portions of the universe are forever beyond our observational reach, how can we claim to have a scientific theory of the universe as a whole? Some philosophers of science have argued that cosmology requires a different epistemological framework, one that allows for inference to the best explanation, and theoretical elegance even when direct empirical tests are impossible. Others have argued that we should restrict our theories to making predictions only about the observable universe, and should be agnostic about regions beyond our horizon. These debates reflect deeper questions about the relationship between mathematics and physical reality, between observation and theory, and between what we can know and what actually is. The discovery in the late 20th century that the fundamental constants of nature, the mass of the electron, the strength of the electromagnetic force, the cosmological constant, appear to be finely tuned to allow for the existence of complex structures, and life has added another dimension to questions about cosmic endings. If any of these constants were even slightly different, stars might not form, or they might not produce the chemical elements necessary for life, or the universe might have collapsed or dispersed before galaxies could form. This apparent fine-tuning has been interpreted in various ways, as evidence for design by an intelligent creator, as evidence for a multiverse in which different regions or different universes have different values for the constants, and we necessarily find ourselves in one compatible with our existence, or as an indication that our current theories are incomplete, and that a deeper theory might explain why the constants have their observed values. The question becomes particularly acute when considering cosmic endings, because the values of the constants determine not just whether life can emerge, but also how long the universe will remain hospitable to complex structures and what its ultimate fate will be. The anthropic principle, the idea that observations of the universe must be compatible with the existence of observers, has been invoked to explain fine-tuning, but it remains controversial. In its weak form, the anthropic principle simply states that we should not be surprised to find ourselves in a universe compatible with our existence, since we could not exist in a universe with incompatible properties. In its strong form, it suggests that the universe must have properties that allow for the emergence of observers at some point in its history. Critics argue that the anthropic principle is not truly explanatory, because it does not predict specific values for constants, but only constrains them to ranges compatible with life, and because the definition of observer or life is itself unclear and possibly biased toward carbon-based life as we know it. Proponents argue that in the context of a multiverse with varying constants, anthropic reasoning is a legitimate and necessary tool for understanding why we observe the particular values we do. The physicist Brandon Carter, who coined the term anthropic principle in 1974, distinguished between weak and strong versions, and also introduced the concept of self-selection effects in cosmological observation. The idea that our position in space and time is necessarily biased toward conditions compatible with our existence. Applied to questions of cosmic ending, this suggests that we find ourselves relatively early in cosmic history, when stars are still forming and energy is available to sustain complex structures, not because early epochs are more common or typical, but because observers can only exist during such epochs. If this reasoning is correct, then attempting to infer the universe's ultimate fate from our current observations is complicated by selection effects, and we must be careful about generalizing from our necessarily biased sample. The question of whether intelligent life can influence or forestall the universe's ending has been explored in both scientific and science fiction contexts. The physicist Frank Tipler proposed a scenario called the Omega Point, in which intelligent life expands throughout the universe and in the final moments before a big crunch, uses the enormous energy available in the collapsing universe to perform an infinite amount of computation, essentially creating a simulation of infinite subjective duration within finite objective time. Tipler argued that this could allow for a kind of technological resurrection or immortality, with all possible consciousnesses being simulated in the final moments before the singularity. The scenario is wildly speculative and depends on assumptions about computation, consciousness, and the physics of collapsing universes that many physicists find dubious, but it represents an attempt to find meaning and hope in cosmological eschatology through technological transcendence rather than supernatural intervention. More modestly, some researchers have explored whether advanced civilizations might be able to extend the lifetime of stars or extract usable energy more efficiently from astrophysical processes. By carefully managing the fuel supply in stars, perhaps removing helium ash and adding fresh hydrogen, it might be possible to extend stellar lifetimes significantly beyond their natural limits. By positioning themselves near black holes and extracting rotational energy through the Penrose process, or capturing Hawking radiation, civilizations might access energy sources that would otherwise be unavailable. By creating artificial fusion reactors powered by hydrogen collected from interstellar space, civilizations might generate energy long after natural stars have burned out. All of these strategies would require technology far beyond current capabilities and would at best delay rather than prevent the ultimate heat death. But they illustrate that the details of cosmic ending might depend not just on fundamental physics, but also on the actions of intelligent agents, if any exist and persist long enough to implement such strategies. The question of whether our universe is a simulation created by more advanced intelligences has gained surprising traction in recent years, partly due to arguments by philosophers like Nick Bostrom, who suggest that if creating detailed simulations of universes becomes possible, and if civilizations that achieve this capability tend to create many such simulations, then simulated universes would vastly outnumber base reality, and we would be statistically likely to be in a simulation rather than in the original universe. If this is correct, then the question of our universe's ending becomes a question about the intentions and resources of whoever is running the simulation. Will they let it run until heat death? Or will they terminate it earlier, or modify its parameters, or allow inhabitants to escape into the higher level reality? The simulation hypothesis is difficult or impossible to test empirically, and many physicists dismiss it as unfalsifiable metaphysics. But it represents one more way in which modern cosmology has converged with ancient philosophical questions about the nature of reality and the relationship between appearance and underlying substance. As observations have become more precise and theories more sophisticated, the expected timeline for the universe's ending has been pushed further and further into the future, from Kelvin's tens of millions of years to current estimates involving timescales of 10 to the 100 years or more. This vast extension of cosmic time has made the heat death seem less urgent and immediate, but in some ways more inevitable and absolute. When the end was expected in millions or billions of years, it was possible to imagine intervention or escape. When it is expected in timescales that dwarf the current age of the universe by factors of trillions or more, it becomes harder to imagine any meaningful survival or continuation. Yet physicists continue to explore possibilities for evading or transcending the heat death, driven perhaps by a deep reluctance to accept that everything must end, that all the complexity and beauty that has emerged in the universe will eventually dissolve back into featureless uniformity. The story of humanity's evolving understanding of the universe's ending is also a story about changing concepts of time itself. Ancient and medieval cosmologies generally conceived of time as either cyclical, with the universe repeating the same patterns endlessly, or as linear but bounded, beginning with creation and ending with divine judgment. The development of thermodynamics and cosmology in the 19th and 20th centuries introduced the idea of time as having a direction determined by increasing entropy, the arrow of time pointing from past to future, from order to disorder. Quantum mechanics complicated this picture by introducing fundamental randomness and the possibility of time-symmetric laws at the microscopic level, even though macroscopic processes remain time asymmetric. General relativity showed that time is not absolute but relative, that it can slow down or speed up depending on gravity and motion, and that in extreme conditions like black holes, space and time can exchange roles in ways that defy ordinary intuition. Recent work on the holographic principle and black hole thermodynamics, pioneered by physicists like Jacob Bekenstein, Stephen Hawking, Gerard de Hooft, and Leonardus Susskind, has suggested that information is more fundamental than energy or matter, and that the ultimate limits on what can happen in the universe are set by information, theoretic considerations rather than thermodynamic ones. The holographic principle states that all the information contained in a volume of space can be encoded on its boundary surface, like a hologram, and that the maximum information capacity is proportional to the surface area rather than the volume. This principle has profound implications for the nature of space, time, and quantum gravity, and it suggests that the universe's evolution and ending should be understood in terms of information processing and transformation, rather than simply energy dissipation. Whether this perspective offers any escape from heat death or simply reformulates it in different terms remains an open question. The intersection of cosmology with quantum information theory has led to new questions about the role of observation and measurement in cosmic evolution. In quantum mechanics, the act of measurement appears to play a fundamental role in determining the state of a system, collapsing wave functions and selecting particular outcomes from among many possibilities. Some interpretations, like the many worlds interpretation proposed by Hugh Everett, suggest that all possible outcomes actually occur in different branches of a vast quantum multiverse, with observers simply finding themselves in one branch rather than another. If this interpretation is correct, then the question of the universe's ending becomes more complicated because different branches might end in different ways, or some branches might not end at all, and the universe that ends is only one particular branch among countless others. Whether such speculation represents genuine physics or metaphysical fantasy is a matter of considerable debate among physicists and philosophers, as this narrative has traced the long history of human attempts to understand what happens at the end of the universe, from Babylonian priest astronomers studying Venus on clay tablets to modern cosmologists analysing cosmic microwave background maps from space satellites. A pattern emerges. Each generation believes it has finally grasped the ultimate truth about cosmic endings, only to have its certainties overturned by new observations or theoretical insights that reveal previously unsuspected complexities. Wainwright, in his Cold Tower in 1894, thought he had glimpsed something profound about the universe running down, but he could not have imagined dark energy or quantum field theory or inflationary cosmology. Kelvin and Clausius in the 19th century thought they had definitively established the heat death through thermodynamics, but they did not know about nuclear fusion or cosmic expansion or black hole evaporation. Even today's cosmologists, armed with general relativity, quantum mechanics, and detailed observations spanning billions of light years, acknowledge significant gaps in understanding, particularly regarding dark matter, dark energy, and quantum gravity, any of which might radically change predictions about the universe's ultimate fate. This history suggests a certain epistemic humility. While we have learned an enormous amount about the universe's structure and evolution, our knowledge remains incomplete and provisional, and future discoveries might reveal that our current cosmological models, however well tested and successful, are approximations that break down in extreme conditions or at very long timescales. The universe has already surprised us many times, with the expansion of space, the existence of dark matter and dark energy, the evaporation of black holes, the flatness and homogeneity of the cosmos, and many other discoveries that were not predicted by theory, but forced upon us by observations. There is no reason to believe that such surprises have stopped, and every reason to expect that as our observational capabilities improve and our theoretical frameworks develop, we will encounter new phenomena that challenge or extend our current understanding of cosmic endings. Yet even with all these uncertainties and possibilities for future revision, the broad outlines of the universe's fate seem relatively clear in the context of currently accepted physics. Absent new physics or unexpected interventions, the universe will continue to expand and cool. Stars will eventually exhaust their fuel and die. Matter will decay or be locked up in black holes. Black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy, in which no complex structures exist and no interesting processes occur. A cold, dark, nearly empty void in which the temperature is infinitesimally close to absolute zero, and the density is infinitesimally close to zero, with nothing happening anywhere for all eternity.